Hello students, in this video we will talk about potential energy today. It is the energy possessed by a body by virtue of its position from the ground or state of strain. So how will we find potential energy? Potential energy can be found if you consider a mass m is taken through a height h. Then you know that the mass possesses a weight mg. It will be acting downward over here, and it is taken through a height h. So work required is equal to mgh. This energy is stored as potential energy. Work done, as we learned earlier, W is equal to force into displacement. Here the force is the weight of the body, and h is the displacement. So W is equal to mgh. That is why we write potential energy is equal to mgh. Potential energy is given as V of h. So that can be expressed as mgh. This potential energy is called the gravitational potential energy, since it is with respect to the earth we are talking about. That is why it is known as gravitational potential energy. Gravitational force can be stated as the negative space rate of potential energy. How will we do that is, for example, we will take the derivative of V of h with respect to the height. That is called gradient. So what will we do? This is d by dh of mgh. So when we do this, we get mg is a constant, so we take out dh by dh. So this is nothing but mg. So this mg is acting opposite to the height of the body, so the height through which we are taking the body, so it is minus mg. So we can say minus dvh by dh is equal to f. So that is the meaning of this sentence. Gravitational force can be stated as the negative space rate of potential energy. Next we will see kinetic energy. Kinetic energy is the energy possessed by the body because of its motion. Kinetic energy of a body of mass m and velocity v can be expressed as Ke is equal to half mv square. A body of mass m and which is moving with a velocity v. A body of mass m. Consider a body of mass m moving with a velocity v. So its initial velocity, let us imagine it is u, and changes its velocity to v finally. So we know that v from the second equation, v square minus u square is equal to 2as. Now if the body started from rest, u is equal to 0. Therefore we say v square is 2as. Now force is nothing but m into a. So we get from here a as v square by 2s. So what will we substitute? M into v square by 2s we will take. Now work done is nothing but energy. So work done and kinetic energy you can equate. Work done is equal to kinetic energy. So work done or kinetic energy can be given as work done is force into displacement. So the same will give you kinetic energy also. That is, force is equation 1, that is mv square by 2s into s. So this s get cancelled. We get kinetic energy or work done is equal to half mv square. Kinetic energy is always a positive scalar quantity. It depends on the frame of reference. For example, kinetic energy of a man sitting in a train is 0 with respect to the train, but has a positive value in the frame of reference of Earth. Kinetic energy of a body is related to its momentum. Okay, so how will we find out kinetic energy is related to momentum? That we will do here. See, kinetic energy is half m v square, but we know that momentum p is equal to mv. So p square, if you write, p square is m square v square. So we can do one thing. This equation you can multiply and divide by m. So we got m square v square in the numerator and 2m in the denominator. What is m square v square? It is nothing but p square. So we'll write p square by 2m. So kinetic energy got two equations. One is kinetic energy is equal to half mv square, and kinetic energy is also equal to, in terms of linear momentum, it is p square by 2m. Now, mechanical energy. Mechanical energy is the sum of potential energy and kinetic energy of a body. Okay, so the total energy of a body is called the mechanical energy. That is the sum of potential energy and kinetic energy. Now, coming to conservation of mechanical energy, it states that total mechanical energy of a system is conserved if the forces doing work on it are conservative. So we learned already what is meant by conservative force. In my another video, there is explanation of conservative forces are given. So those who want to know about conservative force can watch that video. Suppose that a body undergoes a displacement delta x under the action of a conservative force F. Then the work energy theorem that says delta K is equal to Fx delta x. Now, potential energy function, we learned in today's video that minus delta V is equal to f of x delta x. In the video, we have taken h as the distance, so we wrote f of h and delta h there. But here, if you are taking the displacement in terms of x, we will put f of x delta x. So from these two equations, equation 1 and equation 2, what we can infer is it's delta k plus delta v is equal to 0, because you know delta k is equal to minus delta v. So if you take delta v to the other side, minus delta v to the other side, it becomes delta k plus delta v is equal to 0. So we say delta of k plus v. What is k and v here? K is the kinetic energy, v is the potential energy, is equal to 0. So k plus v is a constant. Delta represents a change in the sum of the energy, mechanical energy. K plus v is mechanical energy. Sum of potential and kinetic and potential energy is called mechanical energy. So change in mechanical energy is 0, or mechanical energy is a constant. So that is the energy conservation proof, mechanical energy conservation proof. Potential energy of spring is the next topic. Let us imagine one end of an elastic spring is fixed and it is stretched or compressed by applying a variable force at the other end. So this figure over here shows this is the original state of the spring where x equal to 0. This is the extended spring, and this one is the compressed spring. So this is the mean position of the spring, x equal to 0 position. If the spring is stretched or compressed through a distance x, a restoring force will be set up in the spring, which is equal to F equal to minus kx. So this how we are getting is from the Hooke's law. Okay, what is Hooke's law? Hooke's law states F, the restoring force in an oscillating body, that restoring force is proportional to displacement, either compression or elongation. The negative sign over here shows that the displacement and the restoring force are in opposite direction. That means when you try to stretch a spring, the spring will develop a force which is acting against the stretch. Or if you're compressing the spring, it will act in this direction. That is, the restoring force will act in this direction. So compression will be along the left side. Here the extension is happening, so X is the elongation is along the right side or towards this direction, and the restoring force acts in the opposite direction. So F and X has a negative direction. So that is the Hooke's law, and Hooke's law can be written like F equal to minus Kx, where K is the proportionality constant, which is known as force constant. Now, so what happens is when we apply an external force, it will be plus Kx direction, because the spring is pulling it towards this side, means we should be pulling the spring on the other side, so as we will stretch it, we will be able to stretch it. So F external will be always plus Kx, F spring force will be minus Kx. Okay, if the spring is stretched through a distance x, the work done required, we can say F external into dx. It's a dot product, F external dot dx. Now let us imagine we were able to extend the spring through a distance dx. So what will be the work done required? It will be dw is equal to F external into dx. Now the spring is coming in the same direction as that of the pull. So that is like we are applying an F external in this direction. The spring is getting extended also in this direction only. So the work done is dw is equal to F external into dx. That is kx dx. On integrating, if you have to find the value of work done for a larger displacement of the spring, we have to integrate it. That is, integral dw is equal to integral kx dx from 0 to x. 0 is this position, as I told you, and this is the position extension happening, that is through x distance. So when you integrate, you know, k is a constant, so integral will be for x dx. X dx integral you have studied, it is x square by 2. So it is k into x square by 2 within the limit 0 and x. So when you give the limits, it will be half k x square. This energy is stored as the potential energy of the spring. Now this shows the graphical representation of the potential energy and kinetic energy of the spring. Where the potential energy is maximum, the kinetic energy will be minimum, and where the potential energy is minimum, kinetic energy will be at its maximum, and total energy will be always a constant. Now we will do a numerical related to the topic we learned already. The question says a shot traveling at the rate of 100 meter per second is just able to pierce a plank of 4 centimeter thick. What velocity is required to just pierce a plank of 9 centimeter thickness? So we have here V1, the first velocity given 100 meter per second. The thickness S1 you can take, it is 4 centimeters. So I'll convert it into 4 into 10 raised to minus 2 meter. Then it has to pierce an S2 which is 9 centimeters, that is 9 into 10 raised to minus 2 meters. You have to find out in which velocity it should be coming so that it can pierce a 9 centimeter. So we know that we studied just now, that is F into S, that is the work done, is equal to half mv square. So what will we do? F into S1 is equal to half into mv1 square. Similarly, F into S2, we take half mv2 square. Then you divide these two equations. So we get half m get cancelled, F get cancelled. So what will we get is S1 by S2 is equal to V1 square by V2 square. S1 is 4 into 10 raised to minus 2 divided by S2 is 9 into 10 raised to minus 2. V1 square is 100 square divided by V square, V2 square. So V2 square we will find out. First we will cancel this. Now 4V2 square is 100 square into 9. So V2 square is 100 square into 9 by 4. And we get V2 as we can say 10 into 3 by 2. That is 15 meter per second. The value F we have taken as the resistance of the plank. That is why we could take it as a constant. And another question. The bob of a pendulum is released from a horizontal position A. If the length of pendulum is 1.5 meter, what is the speed with which the bob reaches the lowermost point B, given that it dissipates 5% of its initial energy against air resistance? So first we will draw the figure how it will look like. So it is the bob of pendulum is released from a horizontal position. So that means it was brought here in an horizontal direction and it was released like that and it reached here. So this is the path through which it has traversed. Its length is 1.5 meters. What is the speed with which the bob reaches the lowermost point? So this is the point A and this is the lowermost point B, given that it dissipates 5% of its initial energy against air resistance. So when it is at this height A, it possesses potential energy, which is equal to mgh. So energy lost is 5%. So that means when it reaches at B, what will be the energy is, energy at B is equal to, only it will possess 95% of its mgh, because 5% of it is already dissipated. So what is the energy possessed at this lowermost point is completely kinetic energy. So the kinetic energy at B is equal to 95% of, meaning 95 by 100 of mgh. To solve this, what we have to do is we write half mv square, because mass is not given for us in the question. Half mv square is equal to, we will write 95 by 100 into mgh. So we know the m is a common factor, it cancels. So we will find out now by giving g's value and h value, we will find out what is the value of v square. So v square is equal to 95 by 100 into GH into 2. So this is 95 by 100 into G, I am taking 10, H is 1.5 meters into 2. So the final result will be V, we will find out, that is 5.28 meter per second. This was V square, and from that we have to find out the value of V by finding the square root.